guys, welcome to the User Shop. It's Marco here, and today I would like to talk to you about a purchase that I've made to upgrade and improve the capabilities of my CNC mill that didn't turn out quite as good as I had planned. So this video is going to be fairly boring for those non-machinist type, and what I'm aiming to demonstrate is the fact that the digital readouts that I have purchased from a fairly good manufacturer did not work out as advertised. These digital readouts for the X, Y, and Z axis are rated with an accuracy of 1/1000 per 6 inches and 1.5 thousandths per 12 inches. I have two 12 inches and one 6 inches. And the accuracy I'm getting is completely off. I'm getting about 7,000 to 10,000 on the Z and X, and 30,000 error on the Y. So if you're not interested in kind of like boring details on how and why these DROs are not working out, then this is probably not the videos you want to watch. If you're interested in this kind of stuff though, hang in there, because I will show you the installation of the digital readout on my mill, and then we'll look at a sample part that I cut that was supposed to be pretty good, and it turned out that the measurements are just not there at all. Also, we'll get on the board and I'll show you a little bit of the ideas of the G code with this particular part, and how I got to the to find out that the digital readouts were at fault. So the mill is over there. I'm gonna turn you around and we'll go take a look at it. Alright guys, so here's the CNC mini mill that you've probably seen in the past in some of my videos, and here are the digital readouts from iGaging. I had the previous version before, which I liked quite a bit. This one's even better because it's an absolute digital readout type. That means that even if the DROs are turned off, if you move the mill in any direction, you turn them back on, it will know where they are, so it will not lose its position, which is a good thing. Let's take a look at the installation of some of the axes. Here attached to the bed, the base of the mill, you can see the Y sender, and let's see, if I move it a little bit, you'll be able to see what it does. And obviously the Y axis is moving. I like it because it got big numbers, and I guess I'm getting older, and I do appreciate that type of readouts compared to the older model. Let's take a look at the Z-axis. The Z-axis is attached to the column, you know, fairly standard. Actually, this top is not really even connected. It's got point of contact right down here. It's attached to the center, and then the bottom is attached solidly to the column. Same idea. As far as the X-axis, I kind of did something a little bit different. One of the problems with the X-axis is it'll get chip contamination fairly easily, so I welded up some aluminum, made a little cover for it, and attached this buffle. It's off right now, but this buffle attaches right there, so no chips fall down there. You can kind of see back there a little bit. Let's see, maybe you can see it from there. We get underneath. You might be able to see it. You can see the bottom sticking out right here. It's attached to this part of the mill, and as the table moves back and forth, this one doesn't actually move, but the scale here is attached to the bed, and it does move. And let me see if I can give you a little demonstration. Just refocus here. Alright, so if we move the x-axis, you can see the color doesn't move. So anyway, that's how that works. And let's turn the controller off because it makes a lot of noise. And let's see, the other day, this is a brand new installation. The other day I was working on a part, and let me just show it to you. This is part of, never mind, this is a unrelated hole. Just closing it so that it doesn't distract you. Maybe that distracts you more, but this plate is part of a pneumatic power draw bar conversion that I'm working on. Let's see, I got a couple of brackets that I machine here. These brackets will sit up on top here, one on either side, and will hold the air cylinder that will move a drawbar up and down. And I think I had an air cylinder. Here's the air cylinder right here. So now this air cylinder will be screwing in there, and this old part will be sitting right on top here with a lever that would push down on this drawbar and open up a collet. So we're just changing the whole system to make it a little more user friendly. So let's get back to this part. This part is designed to be, the original part is supposed to be 3.45 inches. I made it a couple of hundred thousandths wider to clear the belt on my of the head there. So this would be 3.65 in width, and 3 inches exactly front to back. This side dimensions are a little more critical than these dimensions. Back and forth is not really a big deal. But let me sit you down here, and I'll tell you, use a caliper, and pardon the shaking. We'll see what we get, and you'll understand the problem. So we're looking for, and this is a eye gauging also digital readout with the known origin. Very nice. Paid about $35. Very smooth action, very precise. So when we measure it, I'm expecting to see 3.65, and right now I'm getting 3.67. Let me do it around a little bit. All right, so we're off by 7.5 thousandths, which is quite a bit. Let's measure this side. This side's supposed to be 3 inches exactly, and instead we get 3.050. So this part is totally off. It's 50 thousandths off. So you can see that there's an issue there, and I was quite mystified about what could have caused this. And the first thing I did, I went back to my my drawing and try to see what could have possibly done that. Make sure I had good numbers here. You can see the top plate right here. That's the part I was trying to make, and you can see the design of the pneumatic drawbar right here. So the part looked to be exactly the way I wanted it in CAD, and I took a quick look at the CAM portion, computer-aided machining, to make sure the G-code it produced was correct. So let me just show you what I was looking for when I looked at the G-code. And so I kind of drew it up there. And let's see if we can talk about this for a quick second. So here you can see the aluminum plate, about 3 inches by 3.65 inches, the way it was supposed to be. The tool is the red tool. It's actually a 1/4 inch end mill. I measured it at 0.251 inches. The origin of the part is right in this corner, and the coordinates I was looking for in the G code when the end mill cutting this part was traveling up was an X of minus 0.1255, which is half of the diameter of the end mill, obviously. As it would turn on this corner, around this corner, I'm looking for 3.1255 in the Y, again an X of 3.7755, and back down below the X-axis I'm looking for minus 0.1255. Obviously the same, since this is just half a diameter or 1 radius below the axis. So when you put those numbers in here, you add 3.755, which is this coordinate from here, this distance from here to here, plus you add the 1.255, you come up with 3.901. Take away the diameter of the end mill, you come up with 3.650. Same thing when you take the distance from here to the x-axis, which is 3.1255, you add half the diameter of the end mill, 0.1255, come up with 3.251, take away the diameter, 251, you come up with a dimension of 3 inches exactly. So these numbers are, those numbers are the one that I looked for in the G code, and these are the exact numbers that the G code produced. So I couldn't quite understand, these are the exact numbers, yet we're 50,000 bigger in this direction and about 10,000 bigger in this direction. That didn't make a lot of sense. So the other thing that I did at this point was to measure this part another 50 times, really. I took another caliper, a Harbor Freight caliper, not the greatest precision, and the numbers were confirmed to be within about 1,000 of the eye gauging caliper. So that left me with a couple of options. It could be that the digital readouts are not reading right, but they're supposed to be precision instruments from a manufacturer that I trust, since I have other devices from them. Or I don't know what else. One of the issues with Mach 3 is that you have to calibrate the different axes, so that for a certain distance, Mach 3 sends out a certain amount of pulses, a certain amount of steps for the stepper motor, so that they equate to this distance. So what I did when I mounted these digital readouts, I used them to calibrate the motor tuning section of Mach 3. In other words, I mounted them, and then I told the mill to move, say 8 inches in the X, and looked and see how many inches the digital readout said that it actually moved, and made corrections for it until I got the same amount that I commanded. So at the end of the tuning up session, if I told the mill to move 5 inches in X and I hit go, the mill would move. Mach 3 digital readouts will say 5 inches, which they really only measure impulses that are being sent out, and the digital readouts on the mill itself, the one from eye gauging, would read 5 inches. So once I reached that, I was happy, and so that's the next thing of test that I did. I just made sure that would work. So I started running the mill in the z-axis, in the x-axis, and the y-axis to make sure that something hadn't happened to make them go off step from the computer. And sure enough, everything worked great, and we're going to take a look at that right now, and then we're going to talk about what else we can could have gone wrong. All right, guys. So we're going to start running into the boring section now, or this even more boring section. We're going to be running some tests, and just want to show you. This is the motor tuning section, and this is what normally gets set. It's a certain amount of steps. In this case, it's 10,018.21867 steps per unit. I think it's an inch, but it doesn't really matter. And that's for the x-axis, y-axis, and z-axis. Each one of them has a different set of values. So first of all, I just want to show you that we have the backlash turned off, and these are not necessarily exact numbers. I was just playing around with this, but the backlash is not enabled. If you don't know what that is about, then that would be a whole separate videos. But you can look it up on my blog. I explain it quite nicely there, I think. What we're gonna do, we're gonna go into the manual digital interface, and we're gonna jog the bed to move in the plus direction to take out the backlash, and so that's where we'll start. So we're gonna 0 the X, 0 the Y, 0 the Z. And we'll give a couple of commands. Actually, let's get to the digital readouts first. And we're gonna zero. We're just gonna zero the incremental portion. There's no need to set the origin. So again, incremental. They're all set to 0. Now, as far as command, we're gonna go some rapid commands. So G is 0. What we'll do, we'll move the let's see, let's do the X. We're gonna move the X in the positive direction to the 2-inch position. So what's gonna happen, Mach 3 is gonna command the motors to turn a certain amount of steps per unit until it moves 2 inches, and you will see 2 inches up there. Again, that's not really a readout of the distance, that's more of a readout of the impulses that have been sent out. What is a reading of the distance is the actual digital readout, which is mounted again back behind this plate, and that measure actual movement. And the reason it is important is that sometimes due to friction, due to moving the bed too fast or hitting a stop, the bed might not move, and while this digital readout thinks that you are at 2 inches, you might not be, and this digital readout actually measure the actual distance of where the table is at, and so it'll be able to tell you whether you're there or not. And you can actually use this number and type them in there to synchronize both the Mach 3 software and the mill itself. So some people don't think that digital readouts are really that necessary on a mill. I find them very useful, but that's a subject for a whole separate discussion. So we're gonna run this and observe what happens. Okay, so alright, so we move 2 inches to the right, and voila, the digital readout says that we move 2 inches to the right. That says we move 2 inches to the right. So far so good. And we're gonna do the y-axis now. Same thing. Let's move a couple of inches. Let's see, G 0, Y. I don't know if I got 2 inches to go, but we'll see. We might end up hitting the stop, but hopefully not. All right, Y2. I'll hit go. All right, so this is one of those cases when you hit one of the stops and and things get messed up. So you can see that this thing is somewhere else, while that thing is at 2 inches. So let me just move it up and run this test again. Alright. I should probably told him go to -2 inches. Alright, zero it out again here. And stuff happens, but G0Y -2. Let's try that again. Alright, this time we didn't hit anything. And I'm having some issues here with this plug. It's not showing any movement at all. This has been a little bit touch and go. I'm not really sure what's going on with it. Let me just disconnect this and attach it down there so we'll be able to see that again. So basically I rewired, took this cable and for the Y and connected to the XDRO. This is just an issue that I've had a few, earlier today. It's got nothing to do with the issue that we're talking about. So we're just going to use this. It's like a loose contact in there. We're going to use this for now, and we'll redo the demonstration. So we can go back to the Y-2 and move that, and you can see 2 inches. The table moved 2 inches. The digital readout says 2 inches. Everybody's happy. Basically the same thing with the Z-axis. I'm not gonna do it right now. So where does that leave me? As far as our part over there, it means the digital readout and Mach 3, they're all running the same numbers. The code that we saw up on the board runs the proper numbers, yet we're still coming up with the wrong part, the wrong dimensions. It could be the details was wrong, but I've used a second one to confirm it. So I was kind of running out of ideas until I thought, what if there's something wrong with this digital readouts? I mean, they are new. I just added them a week or two ago, and I haven't really had much time to test them. So I rigged up another test, and I'm gonna run it for you now. I'm gonna set up the machine that we're gonna run the test, and with this test I will show you that these digital readouts are completely wrong as far as what they tell me. Yes, they are synchronized with this, yet they're not running in inches. Basically, I'm running in made-up inches, because when we put different different dial indicators, we're going to use all three of those. When we use those dial indicators, we will see that we do not get the same numbers as those. So let me set up the test and let's take a look at it. Alright, here we go with test number one. Test number one, we have an hexagonal bar in the spindle, and this is 2 inches dial indicator, and we're gonna take up a little bit of the slack zero out, the digital readout. Oops. Move 1/1000 at a time. And again, I'm showing you the whole thing just so that you see there's no tricks here, as far as what's going on. We're gonna zero the X readout. Alright, and we are going to zero Mach 3 readout. Then what we're going to do, we're going to send it to 0x. Let's see, we're moving the 2 in that direction, so x plus, let's do 2. X plus 2. Alright, I'm going to hit go and let you look at it, and we'll see the numbers that you read here and the number that you read there should be identical. they're measuring the same distance basically. So let's let me see, where's the enter key. Let's hit it. Let's take a look at it. Alright, we get 1.995, so half a thousand off. That's great. That one says 2, of course. And let's go take a look at what our indicator shows. Indicator shows about 2 thousandths off. That's actually not that bad. I have had it show actually worse before, but when you think about it, we're looking at 2 thousandths here, actually 2.5 thousandths, because we're going to 19, 9, and 5. So 2.5 thousandths over 2 inches, while our accuracy over 6 inches should be 1/1000. So over 6 inches, 1/1000. We are 2.5 over 2 inches. That makes us times 3, so 6, 7, 7.5 thousandths off versus 1/1000 that it should be. But let's try the other two digital and analog indicators and see what we get. Right. X-axis test number 2. I got our analog indicator here, and let me jog it, take out the backlash here. Should be getting there pretty soon. Actually, I'm going the wrong direction. Never mind. And 1 more thousand. Alright, so we're good to go with that. And alright, we're going to zero this, and we're going to 0 Mark 3. This is over out. This time we're only going to run it 1 inch because that's a 1 inch indicator. So let's go, sorry, X1 inch, and let's see if I can keep you up there. Well, let's just look at this first. Alright, so I didn't hit the G0, so it's moving at feed rate, but that's good enough. Let's see. Alright, so get exactly 1 inch up there, exactly 1 inch up there, and that looks like 2 thousandths off. Alright, again, 2 thousandths over 1 inch is supposed to be 1,000 over 6 inches, so we're like pretty bad. So I set up a little G code that will go to minus 650 inches, 650,000 of an inch, back to 0. It'll show the backlash. Go to 0.100 and back to 0. The needle should be zeroed out, and then it does it a bunch of times, and you'll be able to see, first of all, that it gets to 650. When it comes back to near 0, you'll be able to see about 2 thousandths of an inch backlash, and then goes back to 0.1, back to 0, and starts over again. And we'll be able to see at the 650 mark, we'll see what the difference is with this digital readout. Again, I took the Y and plugged it in the Z because I got an issue with the plug here. So let's just start the code. Alright, go to 650. Try to get you right over the top of it. Where is it? Yeah, back to 650. Right on it. Backlash 2 thousandths. Back to 0. 650. Backlash 2000. Back to 0. 650. Not quite. Backlash. Back to 0. Minus 650. So you got about 9,000. Alright, backlash. 0. 650 again. So it's about 9 thousandths 9 thousandths off. And let's take another look at this guy. 650, 2000 backlash, back to 0, and 650 again. So even after doing it, I don't know how many times, it's like probably 10 times, this is right on, synchronized with that. Now 650, back to 0, which is 2000 backlash, 100,000 back to 0, and that's the end of the code. So we obviously have a pretty big issue with the Y indicator. Well, it says Z, remember, it's connected to the Y, which is down there. And you know, pretty much all of the axes have some issues with these indicators, so I'm not very happy at all about them. And I'll talk to iGauge and see what they say about it. We're running the same code. Zero out the Y axis, zeroed out the, remember, the Y axis comes to this indicator, and I'm using a different indicator now. This one is 2 inches long, and it zeroes out to the side here. So we're gonna run the same code as before and see how this one fares. Off it goes. Going to 650. And let me zoom you in here in a sec. Alright, back to 650. That's almost right on. 2000 backlash. 0. 6, about 5 thousandths off there. 2000 backlash. Back to 0. So you get the idea. Let's look at it here again. Alright, should be going to 0. There you go. Now 650. It's still off by 8.5 thousandths. So this is a completely different indicator, and demonstrating the same trouble. It's about 0.5 thousandths off of the other indicator. Again, let's just look at this. 650, 0, which gives us backlash, and cycle back to 0. And so now we got two indicators confirming within 0.5 thousandths of each other, while this is still off by 8.5 to 9 thousandths of an inch. So obviously there's quite a big issue with these devices. And let's try another. We're rerunning this part. We're rerunning this part with the same code, same holding, but after synchronizing the digital readout on Mach 3 with the 2-inch long dial indicator. And it seems like it's starting to cut back here. Got a little bit of a chamfer right there to go through first. Should be, now it's I think 20,000 lower, so it should start cutting a little bit more. And sure enough, looks like it's taking off. Looks like it's taking off the excess. Right there we have 49, 50,000 excess. So rerun these parts and then remeasure it, and it should be a lot closer. Well guys, I hope I proved to your satisfaction that those digital readout are not good enough to be on a mill, at least on my mill. I know I proved it to my satisfaction. So what I have done, I have recalibrated Mach 3 using this 2 inches I forget the name now, but another revelation is that the 2 inches dial indicator and the 1 inch dial indicator, they agree within half a thousand, so they're both pretty good. So now for the final reveal, I have after readjusting the motor tuning to the specifications of the dial indicator, I've recut our plate, and there it is. Even the thread works now, which is kind of amazing considering the hole was a little bit of a oval shape, not quite round. So I'm gonna use the caliper now, and we're gonna measure this one last time, and you'll make up your own mind as far as what's the better way to do it, and I'll just leave it at that. Alright, so there's our plate, and we use the digital caliper. It's, again, 3 inches, 650,000 we're looking for, and we have here, we're about half a thousand to maybe 1,000 off. We overcut by, it looks like 1,000. Oh, sorry, let me just grab that. There you go. All right, maybe 1,000, 1,500. Certainly better than 10,000 off. And this side is supposed to be 3 inches exactly. And again, we kind of overcut it by about 1,000. So 1,000 off on the 3-inch part, over 3-inch part. I'm pretty happy with it now, and no thanks to the digital readouts from my gauging. So needless to say, these things will come off my mill. Hopefully I'll send them back. We'll see how it goes. Grizzly again said that they had nothing to do with it, and they want me to talk to iGauging. So I'll be calling iGauging again on Monday and see what they got to say. But I'm not hopeful. For about $250 that I spent on these things, I'll have to maybe chuck them, but I won't be using them anymore. So guys, in conclusion, I spent 3 days working on this problem, and I've finally figured out what the issue is, and my digital readouts are just not good enough for the kind of work that I need to do on the mill. So the good news is that the mill is really solid. I was led to believe, based on those on the readings from the digital readouts, that my mill was a little bit wishy-washy, if you wish, but it was actually the digital readouts that were not accurate enough, not repeatable enough, and you know, I'm sure by now you have your own opinion on whether you want a set of those on your mill or not. So I hope this has helped somebody out there. Once again, use a good quality dial indicator to tune the motors on your mill, and then go with that. There's no need for digital readouts that are just going to complicate your life. And all you have to do is just go online and just do a search for you know, iGauging digital readouts problem, and there's a lot of posts out there for things that you can do to make them a little better, but it doesn't seem like you can quite get them to the level of precision that is necessary. And talking about precision, I have settled on some values of backlash for all 3 axes of 1.2 thousandths. So I'm very pleased with that, considering that I thought I had 4 thousandths of backlash before. I'll take 1.2 anytime. So again, I know this has been a little bit long, a lot of material, and it was a bit of a journey for myself as well, since I didn't really know the way things are going to end up at the end. I hope you enjoyed it. I hope you got something out of it. And once again, welcome to the Easy Shop. I'll see you next time.